Alright, so in order to study the physiology of the body, we need to learn a little bit of chemistry. You may have already seen the word chemistry on the screen and started to panic, but studying anatomy and physiology without understanding a little bit of chemistry is really boring, and you're just going to end up trying to memorize a lot of stuff that doesn't make any sense. And if you can understand a little teeny bit of chemistry, and I promise you I'm going to go very, very, very easy, almost non-existent on the math, then you can actually start to figure out how these amazing processes in the body are actually occurring. And my guess is if you studied any chemistry, it's pretty rusty, or maybe you really don't remember it at all. So we're going to go back and refresh our memories on some chemistry. And what we're really going to do is focus on water and some of the other most important parts of chemistry to actually understand physiology. And then by the end of this lecture, you should have enough chemistry understanding to start to really figure out how the cellular membrane is structured and how stuff crosses over that cellular membrane and why. And so much of the body processes have to do with the magic of what happens over the cellular membrane. So chemistry, the chemistry in the body, I mean, everything that happens physiologically can be thought of as liquid chemistry, or you could say wet chemistry. In order for all the chemical reactions to happen in the body, they need to be in solution. So, in other words, biological molecules, or the molecules in our bodies, do not react unless they are in solution. And almost all of the chemical reactions that happen in our body depend on water. So water, I'm sure you've heard water is essential to life, and I'm sure you've heard people tell you that you need to drink lots of water, and before long you're going to be telling your massage clients to drink water, but why? Because I said so. Okay, that doesn't work super well, so why really do we need to drink water? Well, for starters, how much of your body inside your cells and outside of your cells, intracellular and extracellular, is made up of water? Well, you've probably heard that some different numbers thrown around, and it actually kind of depends on age and various factors, but about 60-70% of our bodies are made up of water. So in order for our physiological chemical processes to occur, the cells inside and outside need to actually be bathed in water. We have a nice salty seawater soup throughout our body, and everything happens. But okay, so our bodies have lots and lots of water. Does that really explain why we need water? To me, not so much. So let's take a look at some of the actual functions of water, or in other words, why is water ideal for supporting life, or why is water so perfect for supporting life? Water has all these amazing properties that are ideal for supporting life: high heat capacity, high heat of vaporization, polar solvent properties, reactivity, and cushioning. That's a lot of big words, and does it make any sense to you? I don't know. let's start with a little video that gives us a preview to some of these properties, and then we will take a closer look at some of the really important characteristics of water that makes it actually able to have all these properties.
Water has been called the universal solvent because it can dissolve many substances. Wherever water goes, either through the atmosphere, the earth, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This is one reason why water accounts for about 70% of the weight of a cell, which is the building block of life. Water has high specific heat, which means it absorbs a lot of heat before it changes temperature. This is why water makes a great coolant. This is also why oceans, lakes, and water vapor in the atmosphere help to regulate the Earth's temperature. Water molecules are sticky. They attract to each other, which is why water tends to flow together, fall as raindrops, and bead up on the surface of a leaf. This property is the result of cohesion. To understand cohesion, let's imagine we're recreating a water molecule. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Because of the molecule's arrangement and the electronegativity difference between the hydrogen atoms and the oxygen atom, the molecule becomes polar. The oxygen atom has a negative charge, while the hydrogen atoms have a positive charge. Since we all know opposites attract, the oxygen atom will stick to a nearby hydrogen atom. The result is a strong bond. Surface tension is a result of cohesion and is the measure of how difficult it is to break the surface of a liquid. We can observe the high surface tension of water by watching this mosquito step onto its surface, or this insect as it struggles to free itself from a droplet. Surface tension is also what causes a water droplet to take a spherical shape. Water is the most cohesive of all non-metallic liquids. Adhesion is similar to cohesion, but refers to 2 different surfaces or molecules with an attraction to one another. This is why the droplet sticks to this leaf. Along with cohesion, adhesion is responsible for a phenomenon called capillary action. Capillary action is the force that pulls water upward against gravity through a narrow tube. This is an essential property for plants, which rely on capillary action to pull water from their roots up to their leaves. So it's pretty obvious that water is important stuff. Humans rely on it for personal consumption, as well as things like industry, energy production, and agriculture. But we sometimes have a tendency to use.
Alright, so let's get back to the properties of water. Okay, so let's talk about what high heat capacity is. So basically it takes a lot of energy to change the temperature of water. It takes a relatively high amount of energy to change the temperature of water. And why this is so great for supporting life is that it actually helps maintain homeostasis, or makes it so that your temperatures inside your body don't fluctuate too easily. For example, if you think about something that would create a lot of heat or use a lot of energy in your body, like let's say something that uses your muscles a lot. So let's say you're exercising, let's say you're sprinting. Your muscles are going to release, they're going to be doing a lot of metabolic activity, and they're going to be releasing a lot of heat. Well, your inside and outside, all of your cells, including all of the ones around your muscles, have lots and lots of water, and that sort of acts like a buffer because it takes a lot of heat to actually change the temperature of water. So in essence, you don't end up like frying your muscles, because the water can sort of absorb some of that heat before it changes the temperatures. And your muscles are made of a lot of protein, and I like to think about how eggs are made up of a lot of protein, and when they're at room temperature, crack an egg, you got a nice soft egg in a bowl, and if you fry that egg up and it gets all rubbery, then that's what would happen to the proteins in your body if they got too hot. So you wouldn't want to fry up all the proteins in your body when you exercised, so the water can help sort of absorb some of that heat before it changes temperature. Now this next fact is similar, it's related, and it has a cool function in the body. Water has a high heat of vaporization. In other words, it takes a lot of energy to take water and transform it from its liquid form to its gas form. So in other words, for water to evaporate, it takes a lot of energy. And your body takes advantage of this system in the way of releasing heat from the body. So going back to the example of exercising and sprinting, or any kind of vigorous exercise that is going to use a lot of muscle activity, lungs, heart, all these things that are going to use a lot of energy. Let's say you're sprinting and you're getting hot, the body can take advantage of how well or how much energy it takes to go from liquid to gas by taking a thin film of liquid, which is mostly water, on the surface of your skin when you sweat. And then because it takes a lot of energy and heat to evaporate that thin film of sweat off of your body, as that sweat evaporates, turning from liquid sweat to evaporating, that actually removes a lot of heat, or takes a lot of heat to wick away that sweat. And so that's kind of a brilliant air conditioning system that your body uses and takes advantage of this high heat of vaporization. The polar solvent properties is one of the properties of water that is just crucial to so many chemical, physiological processes in the body, that as soon as we go through this list, we're going to watch some short videos and talk about exactly how and why this works. But polar is basically like a magnet with a positive and a negative side, and water having a positive and negative polar charge is sort of the basis for much of how water is able to interact in the body, including why it makes such an excellent solvent. Water is reactive, or has reactivity. In other words, it is used in a lot of chemical reactions. So not only is it a solvent, in other words, materials can be dissolved in it, but it can actually be used in chemical reactions. And probably the most common kind of chemical reactions that happen in the body, where water is actually sort of added to the equation or used as part of the chemical equation, is decomposition reactions. For example, to digest food into the smaller bits that we can actually absorb. Those kind of catabolic breaking down decomposition reactions are also called hydrolysis reactions, hydro for water. So it actually uses water, so in other words, adding water to actually break down those foods into digestible bits. So that'd be a brilliant reason to take in some water. And then cushioning, water can actually provide, you know, a buffer or cushion so your organs and things don't get hurt. So for example, around your brain and spinal cord is something called cerebrospinal fluid, and that has water and a bunch of nutrients dissolved in the water, and that actually makes it so that as you you know, have kind of jarring movements to your head and your spinal cord, that those very precious vital organs are not, you know, sort of smacking into the bones. Like, say you were on a roller coaster ride and it was a real jostly ride. The cerebrospinal fluid actually cushions or buffers it so that you're not smacking into the sides of the walls of the bones. But of all of these amazing capacities, one that we have to really understand for practically, I mean, just so many chemical reactions, I'd have to think about all of them before I said for sure if it was practically all of them, but so many of the chemical reactions in the body depend on this water's polar properties, where the H2O, the hydrogen side, has a slightly more positive charge, or it's partially positive, and the oxygen side is partially negative. So we have a more positive side and a more negative side, so it acts like a magnet. And much of how water behaves and how it is a solvent and how it interacts in a lot of situations is because of this polarity. So let's take a closer look at that.
Formula for water, H2O. A model of H2O doesn't look like much. Two small atoms of hydrogen, H2 part of H2O, attached to one bigger atom of oxygen, the O part of H2O. Kind of like a cartoon drawing of a teddy bear. And actually, water is kind of funny. Fun facts. In water, just so you'll know for later, the H's and O's are held together by covalent bonds, by sharing electrons. H2O is a polar molecule. The same way our planet has north and south poles on opposite sides, the H2O molecule has two poles on opposite sides. And like a magnet, H2O has one positive end and one negative end. Thinking of that cartoon teddy bear again, the chin side of the oxygen atom has a slight negative electrical charge. The opposite side, the side with the two hydrogen ears, has a slight positive electrical charge. This might just be the second most universally known bit of chemistry. Opposites attract. The positive hydrogen side of every H2O molecule is going to attract and be attracted to the negative oxygen sides of other nearby H2O molecules in all directions. More and more of them pull closer and closer together until they're like people in a hot, crowded dance club. Packed so close together they can hardly move, but still turning and moving wildly. Molecules that stay close to each other are called cohesive, and water is highly cohesive. A pentillion, even hextillion of chaotically moving, tightly packed H2O molecules cohere to make a single raindrop. As good as water molecules are at all this cohering and convening, they also form bonds with surfaces and molecules unlike themselves, a force called adhesion, as in adhesive. Pour the water out of a glass, and the inside of the glass is still wet. Some H2O molecules stick or adhere to the silica molecules in the glass. Being cohesive and adhesive is what makes water a near universal solvent. How? Take salt or sodium chloride. Sodium ions, abbreviated as Na+, and chloride ions, abbreviated as Cl-, in a crystal. As soon as a salt crystal hits the water, it's rushed by a molecular mob of H2O molecules that break it apart, separate the sodium and chloride ions, kind of a chemical divide and conquer. Because sodium ions have a positive charge, each one is swarmed by H2O molecules flying at it with their negatively charged oxygen sides, completely surrounding the sodium ion, isolating it, carrying it off in a turbulent sea of H2O molecules. The same thing happens in reverse to the chloride ions, which have a negative charge. Each of those is surrounded and isolated by H2O molecules leading with their positively charged hydrogen sides. Each salt crystal is broken into tiny pieces, dissolved by and into the water. There's much, much more to know about H2O, but still turning and moving wildly.
All right, so that is all true, but let's take a closer look at how that works exactly. Okay, so taking a look at how water is a universal solvent. A solvent is a substance in which another substance is dissolved and forming a solution. For example, like coffee, when you sprinkle some sugar into it and the sugar dissolves, in that example the coffee would be the solvent and the sugar would be the solute. Because water is polar, it dissolves substance as well. And being the universal solvent, the reason it gets that nickname for water is that more substances can dissolve in water than any other substance. So more substances can dissolve in water even than super acidic substances or intense corrosive chemicals. Water can dissolve even more than more different kind of substances than even super acidic or corrosive substances that we make. So let's take this step by step, and there's going to be a few things here that I explain in a little bit more detail than the little videos we watched. So we've kind of been exposed a couple times now to the idea that water molecules are polar like a magnet, where they have a side that's more positive and a side that's more negative. And so the side with the hydrogen molecules are going to have a partially positive side charge, and this little symbol right here means partially. So the hydrogen side, or the little ears of the teddy bear, are going to have, or the Mickey Mouse, are going to have a partially positive side, or partially positive charge. And the head or the mouth of the teddy bear or the Mickey Mouse is going to have a partially negative charge. And that, of course, is the oxygen side of the molecule. But why is this exactly? So there's between the hydrogen and the oxygen, there's a polar covalent bond that forms. And so let's break down what this means. And for this, we're going to need to go and actually talk about electrons, electron shells, valence electrons, and the various types of bonds. And we're going to focus on covalent bonds and polar covalent bonds. So the hydrogen and oxygen molecules or atoms are going to form polar covalent bond. Now, a covalent bond means that the atoms share electrons. So in a covalent bond, the atoms share the electrons, and when you add the word polar to the covalent bond concept, it means that the atoms are going to share the electrons unequally. So in covalent bonds and polar covalent bonds, atoms share the electrons, but in polar covalent bonds, the atoms are going to share the electrons unequally. Let's take a look at how and why that happens. So, first of all, why do atoms even share electrons? What does that mean? Why do they do it? Well, basically, atoms are unhappy unless their outer shell of electrons is full. What in the heck am I talking about? Alright, so here's a very simple diagram that is just representative of this little black circle with these two little dots is representing how electrons would sort of orbit around, sort of like the rings of around Saturn. They would sort of orbit around the center, or the proton and neutron of a atom. And they'll call these electron shells, and probably the simplest way to think about them is like orbits. More modern chemistry and physics describes it in a slightly more complicated way, that it's a very similar concept, but it's a little bit more difficult to understand and explain, that rather than sort of like these little electrons spinning around like, planets orbiting the sun and spinning around, that it's actually sort of like can be calculated as like probabilities of where these electrons might exist at any given time. But basically, there's like these different energy levels, or you could think of it of like orbits of like, okay, so in the first shell, or the shell of electrons closest to the center, it's going to want to fill with 2 electrons. So if this is a smaller atom and it can only have up to 2 electrons, it's going to be happy when it has 2 in this inner shell. Now, this inner shell can only fit 2 electrons. So if we have something bigger, a bigger atom that has more than 2 electrons, they're going to get pushed out. It's like going up to the next level of a game. So they're going to level up to the next level, and so beyond 2, like 2 is full. It wants to have 2. After 2, it's going to the next level. So if it has more than 2, the next level likes to be full at 8. So if it's going to be happiest when it has 8, and if it has less than 8 or fewer than 8 electrons, it's going to be unhappy. It's going to be unsatisfied, and it's going to want to borrow electrons from another atom to fill or stabilize that outer shell. So basically, depending on the size, it's basically going to just want to fill whatever is the ideal number of electrons in the outer shell. And in the body, we're mostly talking about the really teeny stuff where it's happy with 2, because if it only has 1 shell, or things with the outer shell of 8, it's going to want to have 8. And they're, bigger atoms, it can get more shells than these 2 shells. So if you get past this second shell of 8, and let's say you get up to 9 and 10, that's going to power up to the next level, but we're not going to be dealing with that as much. We're mostly going to be dealing with first shell full at 2, second shell full at 8, and in fact in the body we're dealing with this shell of 8 so much, people will sometimes talk about a rule of 8. So our problem lies where if we have fewer than 8 electrons, it's basically going to be unstable, and it's going to make it chemically reactive, where it is sort of desperately seeking more electrons. So if you think like a set of anything, like let's take a box of markers, and it's a box of 8 markers. Let's say you lose a marker or two, and you have this great, nice looking Crayola box, and you only have 6 or 7 markers in it. Even though you've got 6 or 7 great colors, and you're still going to be, kind of feeling incomplete now because your box is no longer full of 8 markers, and you're going to be looking for filling out the rest of that set. Here we have an example of fluorine, and in the outer shell we only have 7 electrons in this outer valence shell, and so this fluorine atom, as it goes floating around, is going to be looking to get an extra electron. And so this is where atoms are going to start to connect with each other so that they can get enough electrons. Now, we are talking about hydrogen and oxygen, and the fact that they're going to bond and they're going to have a polar covalent bond. So covalent, again, means that they're going to share electrons, and polar means that they're going to share those electrons unequally. Why would they share their electrons unequally? Well, this has to do with a difference in electronegativity. So every atom has a certain electronegativity, which basically means how strong of a pull or how desperate of a need it has to get its electrons. And you can look at the periodic table of the elements, and you can calculate what each element's electronegativity is. Basically, I mean, you can go the higher up and to the right you go on the chart, the higher the electronegativity. We are not going to be doing calculations, and I am not going to make you memorize the electronegativity in numbers, but understanding it as a concept can help you understand how these polar covalent bonds form. So here on the left in red is represented oxygen, which has an electronegativity of 3.5. And here on the right, the H, the electronegativity of hydrogen is 2.1. So the electronegativity of oxygen is 3.5, hydrogen 2.1. You can subtract the 2.1 from 3.5. So the oxygen has a bigger pull on electrons, and you get a 1.4 difference. So basically it means that the when the oxygen and the hydrogen share electrons, because oxygen has the bigger pull on them, while they are going to share those electrons to try to both fill their outer valence shell and get 8 and get a nice full set of markers, oxygen is basically going to have a stronger pull on those electrons than hydrogen. So it's not going to share it equally all of the time. So let's say they were playing tug of war. Oxygen is on those electrons. Oxygen is going to be pulling those electrons a little bit stronger, it's going to get those electrons a little bit more often. It's like somebody on a basketball team who's kind of a ball hog and doesn't share the ball very well. So they're maybe going to be like dribbling the ball a little bit longer and not throwing it to their teammates as often, and try to make all the shots themselves. Now, since we're going to go super chemistry light here without math, I'm not going to be making you do calculations or look at a bunch of different molecules, but I think it's kind of interesting to note that when you take this simple, subtracting the electronegativity of hydrogen from oxygen and you get a 1.4 difference, it is this number here in the difference between their electronegativity that actually determines if we're going to be sharing things equally, like a covalent bond, or slightly unequally, like a polar covalent bond, or if they're just not going to share them equally at all, and one's going to get it and the other's not, which would be an ionic bond. So chemists have actually figured out, with the different numbers of, different ranges, whether it's, if it's a 1.4, that puts it in the polar covalent range, and, that there's different ranges. It's going to mean it's going to be an ionic bond where one gets the electron and the other doesn't, or polar where they share them but in unequally, or covalent where they share them equally. This has a lot to do with why this polarity, so these partial charges determined by this unequal sharing of the electrons, has a lot to do with why water then becomes an excellent solvent. So because there's a partial positive charge on the hydrogen side and a partial negative charge on the oxygen side due to the difference in electronegativity, this is going to mean that the hydrogen's side, being slightly more positive, is going to be attracted to the oxygen sides of other molecules that are going to be slightly negative. They're going to pull on each other, and the bonds that happen between those partial charges are called hydrogen bonds, and this has to do with part of why water then is such an excellent solvent. And we're going to actually break this down a little bit too, but this gets into the water is basically, because of their polarity, they're going to tend to form the hydrogen bonds, and that's actually going to make the water molecules stick to themselves, which is called cohesion, and stick to other things, which is called adhesion. So basically, here we have some sodium chloride, the Na for sodium and Cl for chloride, like a salt crystal, and the water, the polarity of the water is going to basically pull out the substances and start to separate the sodium and chloride. So the slightly positive and slightly negative charges are going to, the sodium here has a slightly positive charge, so the water molecules, the slightly negative side of the water molecules, are going to pull that sodium out, and then it's going to surround it. And then vice versa with the chloride, which has a negative charge. So the positive sides of the water molecules are going to attract and pull out the chloride side and then surround it. And we're going to take a different look at this. So let's take another look at a different look at how these hydrogen bonds work. So let's take a look at this. Alright, so let's take a little review and look at these hydrogen bonds again. Alright, so let's take a little review and look at these hydrogen bonds again, and how this influences the polar covalent bonds, how this influences water being a good solvent. So again, there's a slight electrical charge in different regions of the molecule because of the electronegativity, and the hydrogen atoms are not able to equally share their electrons in a covalent bond. So remember that atoms with higher electronegativity have a greater need for electrons. In other words, they have a stronger pull on the electrons. In fact, when those atoms connect with other atoms, the ones with the stronger pull on the electrons, they're going to pull them towards them more often and more closely. And I use the analogy of tug of war. Or here's a different analogy. You can imagine a family that shares one car. If one person is in charge of taking the kids to school, they're going to get a and the other person lives on goes to work where it's on a more convenient bus route, then even though they're going to share that car, the person who works at on a bus route is not going to get the car as often as the person who needs the car to get to work and to take the kids to school. So they're going to share that car, but they're not going to get it the same amount of time. And that's similar to how atoms with a higher electronegativity are going to have a bigger need for the electrons, and they're going to get them more often. And this again is how an unequal sharing works with polar covalent bonds. And it's because of this that the molecules then have a positive side and the negative side. Obviously, opposites attract. And then looking here at the diagram on the left, here is how the waters, therefore, with their slightly positive hydrogen side, slightly negative oxygen side, are going to attract each other and form hydrogen bonds. These hydrogen bonds have a lot to do, going back to the properties of water, not only their ability to be excellent universal solvents, but also how they have that high specific heat, as well as their high heat of vaporization. Because in order to change the temperature of water, you basically have to first break these hydrogen bonds. Water has a slightly glue-like property that help hold the tissues of the body together. So this also has to do with the polar covalent bonds, and therefore which also create the differences in charge, then also create the hydrogen bond formation. So this slightly glue-like property, how the water sticks to itself, therefore with these hydrogen bonds, is called cohesion or cohesive ability. So cohesive is how it sticks to itself, how the water molecules stick to themselves, and then similarly, adhesive is how it sticks to other things. So the cohesion, how the water sticks to itself, is what creates the surface tension. So how little water strider bugs can stand on top of water, how water tends to form droplets. And the adhesive ability is how it's going to stick to other things, so like when water forms on other substances, like on windshield of a car. And both cohesive and adhesive properties also are going to help pull the solutes into solution to dissolve them. So that attractive property, how it sticks to other things because of that positive and negative charge, is going to help pull those solutes into solution, like the example of the salt. This actually leads nicely into where we're going to go next. In our next lecture, we're going to take a pretty close look at the plasma membrane, or the cellular membrane, which is made up of a phospholipid bilayer. And this phospholipid bilayer is a brilliant design for how much water is inside and outside of the cells. So each phospholipid molecule has a head that attracts water and a tail that repels water. And like many things, much of the chemistry in the body, this has to do with polarity. So the head that attracts water, the attracting water part is called hydrophilic. In other words, water loving. And you may guess, well, what might make it actually attract the water? If you guessed anything to do with charges, positive and negative charges, polarity, you're right. So a molecule that is polar, that is charged, is going to attract water, or water is going to attract it. And the hydrophobic tails, hydrophobic means water hating or water fearing, water repelling. It's not going to attract the water. That is going to be a non-charged or non-polar side. And so here we have a phospholipid bilayer arranged with the water on the outside of the cells and water on the inside of the cells. Much of this is to do with the charges of the molecules. So let's take one quick little look at a Bill Nye the Science Guy video that he's going to show you quick experiments about how cohesion and adhesion work in the body, and then we'll recap the properties of water.
Okay.
Ordinary dish of water may look like a pizza pan to you. Please
It
stay on the
does.
side.
Looks a lot.
Secret powder, lycopodium powder from the lycopodium plant in the swamps of Britain.
Really?
And I put it on here not for any reason, just
This is
so you can see.
lycopodium powder from British plants, you say?
That's right.
Okay,
You can
once
see
again.
the surface of the water,
Okay.
right?
Yeah, now it's all dusty water.
Dusty water, indeed. You've crystallized my thoughts. Now that is soap from the King washroom, John. Now this
Whoa.
happens very quickly.
I think I'll put on a balloon to handle this then.
John, don't worry. I've got it under control. So
Okay,
after a fashion. And so watch this very quickly.
Okay.
Soap from the King washroom.
Whoa! Ladies and
It
gentlemen.
happens so fast, it happens virtually at the speed of sound.
Okay.
Now, John,
What
that
is it?
principle, surface tension being broken, surface tension, water is grabbing on because
Yeah,
of the
yeah.
asymmetrical molecules. They're like Mickey Mouse ears. They're grabbing onto each other. Okay, now, the
We've got a little
Motorboat.
little boat here
motorboat.
that Bill
and
is
we
going
have-
to attach glue to because
That's
he
right.
says that glue can actually power the boat.
Oh,
Well,
boy.
actually,
Disaster.
Got a disaster. But
Yeah.
look, the boat is actually moving.
Oh, there. It's
Look,
flying.
it's going.
flying.
Just because he's put glue on it.
So it's breaking surface tension, and that is driving the surface tension motorboat around in circles.
Look at
Yes!
that. That's very incredible.
All right, so let's recap here the properties of water. Computer seems to be timing out here. All right, so just to recap, basic chemistry as it relates to the body. A lot of the chemistry of the body has to do with the positive and negative charges of molecules, their polarity, and much of the body's chemistry has to do with water. About 60 to 70% of the body is made up of water. A lot of these chemical reactions happen in a liquid medium of water. I shouldn't say a lot of them. All of the body's chemical reactions have to happen in a sea of water. So these chemicals even being able to interact has to occur in a sea of water. But why else is water so great and so perfect for supporting life? The high heat capacity, again, basically, in order to change the temperature of water, you need a lot of energy. So this can help your body maintain a stable temperature because it requires a lot of energy to change the temperature of the body. It takes a lot of energy to change water from a liquid to a gas. So high heat evaporization. So this is great for the body to cool itself down. So you can form a thin layer of sweat on the surface of the body, and then in order for that sweat to be wicked away into the atmosphere and evaporate from liquid to gas, that requires a lot of energy, a lot of heat. So that heat then gets carried off of the body, which is an excellent cooling system. And then this is one of the very, very, very most important properties of water and how it relates to so many chemical reactions in the body, the fact that it is a polar solvent. So solvent, it is not just a great solvent, it is the best solvent, it is the universal solvent. So more substances can dissolve in water. I can spell universal solvent. So more substances can dissolve in water than any other substance, and it's largely going to be substances that have a charge, that are polar, are the substances that are going to be able to dissolve in water. So things that do not have a charge, like fats, like lipids, they're not going to dissolve well in water. So if you've ever added oil and water and seen how like a film develops and how they don't really want to mix together, that's because there is not a charge on those lipids or those fats. But things with a charge want to dissolve in water. And this polarity, the fact that it has a positive and a negative charge, the little hydrogen, ears having a positive side, and that's a partially positive charge, again, because of electronegativity, and then the oxygen side having a slightly negative charge because it has a higher electronegativity, so it kind of hogs the electrons, pulls them towards it more often and closer. So this slightly positive, slightly negative charge is going to make water perfectly suited towards attracting other molecules. Since opposites attract, positives are going to want to attract all sorts of molecules that have negatives. And the negative side, the oxygen side, is going to attract all kinds of molecules that have positives. And all kinds of molecules are going to have little positive and negative parts. Like proteins, for example, are giant, giant, giant molecules. Lots and lots and lots and lots of amino acids strung together. And on those big, long chemicals, they're going to have little parts of them that are positive and little parts of them that are negative. And that's going to help those oxygen molecules interact with them, and the hydrogen, and so the oxygen side and the water side, positive and negative, interacting respectively. Water, aside from just being a good solvent, it's going to be a crucial part of chemical reactions in itself, and I gave you the common example of hydrolysis reactions, where when you break down a substance, like digesting food particles into small enough parts to absorb them, you actually have to add water to the substances to break them down, and that is called a hydrolysis reaction. And then water also helps cushion the body to protect organs. So there's way more to chemistry than that, and as we go along and study different systems in the body, we'll take these basic concepts and then start to look at, sometimes it's important, these little, positive and negative charges. What does this do in solution, and how do you get stuff with more positives? Oh, they might be more acidic, and these things with more negatives, they might be more base. And so, there's other things we'll need to look at, like acids and base and the pH schedule, scale, and things like that. But I think if you can start to get a grasp on slightly positive and slightly negative charges and how and why that happens, so much of the body chemistry happens because opposites attract. Thank you for giving a good try at understanding some chemistry, and feel free to write in if you have any questions, or we'll work on this some more in class together.